start. My name's Cody Maloney, and I'm going to be talking to you about C++, and specifically how to write good C++. I'm not going to be focusing on how exactly you write the code for a template, how you define variables, how you add things. I assume a little bit of knowledge of C, because C++ is pretty much a direct superset of C, but that's about it. If you want to know how exactly you declare variables and things, there's lots of good tutorials online. What I'm going to be focusing on teaching is how you write good C++ style, which by Bjarne Stroustrup, who's the inventor of C++, he argues that one of the biggest problems in computer science is that we don't teach really good coding style. And you'll see a couple examples that I pulled. This talk is sort of a compilation of talks by him and Sutter, along with some other miscellaneous points. Most of their talks are about C++ old to C++ 11. This talk starts off with mainly just C++ 11 things, as well as base C++ things that will be useful as you go through different classes, and why you should be writing in C++ over C for most of what you do. C++ aims to be, in no case, it aims to give you a high level of abstraction without compromising efficiency. Nothing you do in C++ makes it slower. In fact, a lot of what you do in C++ makes it a lot faster than the equivalent C code, like the sort of example I'm going to give later. So first I'm going to talk about why you might use C++. Next I'm going to talk about things that C++ gives you. Then I'm going to look at some specific examples in C++ of how you do things, specifically some nice things that C++ 11 make easy, and how you can use the language in order to make things happier. And then I'm going to give some miscellaneous insights. If we actually go through all of this, it'll take about 2 hours. How many of you guys are up for staying for a while and hearing about it if you find it interesting? If not, I can cut it short.
I'd like to hear it. I'll stay
So basically, the vast majority of it is in the first 3 sections, which should take about an hour. So if you're interested in leaving around there, feel free. I won't be offended or anything. C++ is a very large language, although it's not nearly as large as, or it's about as large as Java, so Python's also about equally large nowadays. The thing is that what C++ gives you is very different than what Python or Java give you. But miscellaneous insights is mainly going to be focusing on patterns of things that people get wrong all the time in C++ and why they're wrong. And really horrible style in C++. So first I'm going to start off with why C++. What's the philosophy behind C++? So this is a quote from Dijkstra, and he says that the tools we use have a profound and devious influence on our thinking habits and therefore our thinking abilities. When you're writing really good C++, it forces you to think about what in the world you're actually doing. When you're writing in Java, or when you're writing in Python or these other managed languages, you just magically get all of these objects and you can build circular references between them and everything just magically works. This isn't actually a really good thing. In C++, you're forced to structure your program a lot more. You have to decide, does this go in the heap, does this go in the stack? You can put it in either, you can always put it in either, and we can simulate all of Java and all of Python in C++. We can literally write code in C++ which looks just like Java. Really horrible idea. You're throwing away a lot of what it gives you. For instance, you'll notice in C++ when you try and copy something 4 times, you'll actually see that you did that, and probably you should have written that a different way so you don't have to. You'll notice that you're using all pointers like Java or Python. You'll notice that everything in your class is a virtual function, Java. There's a reason why they have to build virtual machines in order to make these things run fast. And they have to build very, very advanced virtual machines, and in order to write high-performance Java, you actually have to stop writing Java purely. You have to start using binaries and things in order to make it run fast. In C++, generally speaking, if you can write it, and it's going to run quickly. There's no inspecting or unstacking C++. There's getting to be more and more introspection so that you can do compile time introspection of objects, but for the most part, things just sort of live in language. In C++, the compiler is very, very pedantic. It wants you to state things correctly, or it won't allow your code to compile, let alone run. This is actually a really, really good thing. We want errors to be compile time errors, not runtime errors. A dialog box telling you that, oh dear God, everything broke is much, much, much worse than having the compiler tell you, this won't compile because you did this wrong. Because these types don't match up. The next thing, and this is from Andrei Alexandrescu, who's a Facebook engineer who is a Facebook researcher. And the going word at Facebook is that recently written C++ just runs fast, which underscores the enormous amount of effort spent in optimizing PHP and Java code. Paradoxically, C++ code is more difficult to write than other languages, but efficient code is a lot easier. One thing to note with this is that he says C++ is difficult. Well, C++ 11, C++ gets a lot easier to write. But generally speaking, C++, if you can write it, it will run fast. For PHP, Facebook had to write a PHP compiler, which compiled it to C++, which then compiled it to native code, in order to make it run as fast as they needed it to. This is an enormous amount of effort, considering you could have just written in C++ and gotten the performance right off the bat. In C++, when you're writing it correctly, you don't have to worry about loose pointers and things. Nowadays, there's not very much good reason to write a raw pointer ever. You shouldn't explicitly be calling new or delete in modern C++. There's one common use case which you should call new, but that goes away with C++ 14, which is coming out next year, hopefully. Because they made a make unique, finally. There's no need for garbage collection in C++. In C++, everything has a deterministic lifetime. We just don't need it. In the vast majority of code that you write, you probably notice, I need this integer for a while and then it goes away. I need this object for a while and then it goes away. And I know exactly how long I need this object for. In C++, we can represent that. And when we have things that, oh, it's going to go away eventually, we can use shared pointers in order to do that cleanly and efficiently. If you are wondering for perf, Google has some really good papers comparing C++ to Java, Scala, and Go. And in all cases, it pretty much finds that C++ is faster, even though all of those programs were written by people who know how to write efficient code in the given language. C++ is still a little bit syntactically heavy, and it makes you write a lot of things which are unnecessary, but they really are working on cutting them out. But now on to a little more of what is C++ and what it gives you as a language, rather than just why it exists. So C++ is existing in order to give you high abstraction without costing you efficiency ever. But what exactly does C++ give you? First thing is that it's a mixed paradigm language. It doesn't force you to code in any particular style. You can code just like you do in C, and it'll probably just compile and work. You can code using classes so that you can get a little bit of encapsulation and build yourself a little bit out of C. A lot of people refer to this as C++. It makes life a little bit better, but it's not really taking full use of language. You can build full object-oriented programming like you can in Java, and you have multiple inheritance, unlike Java, so you can actually represent some things. Multiple inheritance actually has meaning. There's actual cases where you need multiple inheritance, so you just need it to be in your language. You don't need it most of the time, but you do need it sometimes. With templates, we can write generic code, or shape code as I'd refer to it. A template you can sort of see as a factory for code. You plug in variables to the template, and then it instantiates it with those variables at compile time. So I know how to write a linked list. All of you have built a linked list in C at some point, probably. In C++, we can write that same linked list, but we can store the body fully typed and give the compiler full information about it so it can build it more efficiently. In addition, templates themselves are a purely functional language, which is Turing complete. Note you probably don't want to use that directly, however, it is there, and people have built a lot of really cool things in template metaprogramming libraries. The other thing is that you can write functionally in C++. You can write very, very functional code. I actually used C++ as the backend for a functional language compiler. And we could pretty much just directly take the code which you wrote in a higher level language, which was nice and simple and easy, add in all the stuff that C++ wanted, and it compiled, which was really cool. But mainly C++ focuses on letting you choose the right paradigm for your problem. Sometimes you need object-oriented, sometimes you need generic. Generic is what I'm going to talk about is templates. They're generic code. Note with templates, I can do pretty much all the same things I can do with object orientation. In fact, there's cases where with inheritance trees, I can either use templates in order to visit the structures generically, or I could use inheritance trees with virtual functions. So these aren't all distinct. They can cover a lot of the same functionality using different styles. You choose whichever one is best for what you're trying to do. The next biggest part of C++, which I mentioned previously, is efficient abstractions. Templates add literally no overhead. There's a lot of people who are like, oh, C++ is big and slow and inefficient. Templates, no overhead. Virtual functions, no overhead compared to function pointers, which is what you'd have to write in C. In fact, a lot of the time we can optimize templates and we can optimize functions in ways that we couldn't optimize your C code, so we can actually make it faster. Classes are literally structs. In the standard for C++, they define them as aliases. There's a couple things you pick up with classes that C didn't have with structs, but all it changes is by default in C, everything is public. By default in C++, everything is private in classes. That's the only difference. When we get to lambdas, lambdas are something that's new to C++, which are really efficient, lightweight functions that you can write inline in the middle of your code. They are literally compiled into just functions. We can choose exactly what we want, how exactly we want something to behave, or we can use the standard behavior. For instance, if I define my own class for big integers, I can define plus to operate on the big integers in order to add them. I can overload and replace anything the standard does with my own behavior. For instance, later I'm going to give an example. In C++, we can make a Python-style print statement. It's really crazy. You don't really want to do it, but you can do it in C++. It gives you the ability to do these things. In addition, if you're using exceptions, there's no overhead if you don't happen to throw an exception. And we can also build compact data structures. And for this, I have a slide from one of Stroustrup's presentations on C++ style. So inside of a true object-oriented language, if we wanted to store a list of something, we first say, I have a list. And that's going to point to the list implementation. And that list implementation is going to say, I have a variable-sized list of things. So we point to the memory that has that. Each of those points to the object, which is stored in each individual address. And you see that in order to look up one individual thing, we had 3 different layers of indirection. That's 3 different pointer follows. That's really, really slow and inefficient. In C++, what we can do instead is build compact data structures. So if we look at a C++ vector, how it's actually implemented is we have a little header which points to the data, and inside of the data block, we just have every object one after the other in line. And this is much more efficient. Later in the miscellaneous insights, I'm going to talk about list versus vector. We actually see that in almost every case where you should use a standard list, a vector is faster than a linked list, unless you have really, really ridiculously big objects. The next thing with C++ is it allows you to represent what you're trying to do very, very purely. So we can encapsulate things inside of classes by making members public and private and variables private so that you can't mess with my state and get me into places where I don't want to be. You can extend the language arbitrarily to make your own data types. And you can effectively build domain-specific languages in C++. With the Stig compiler, which I mentioned earlier, we literally wrote the Stig type system in C++ types so that you could natively program in Stig in C++. You added 2 optional types. We had optional and some types if you're familiar with those. We'd add them, it just worked. This was really, really pretty. In addition, for things like a big integer type, unlike Java where you have to do .add because you don't have operator overloading, you can just plus them together and it'll work. We can even do a big integer plus a regular integer equals a big integer and related things. We can also have user-defined literals, so we can build types into numbers. So for instance, for a spacecraft, I might want to know the speed of the spacecraft. I might have that it moves 100 meters divided by 9.8 seconds. That gives me meters per second as a type. That's the type of speed. Everything matches at compile time, no overhead at runtime. At the same time, I haven't hand-coded all of these integers and made sure that I do all of the conversions by hand, which I will likely forget. If I tried to do something like feet per second instead as speed, it will convert it to meters per second for me because it knows what the conversion factors are. You can code C++ to do all of this and make it a lot safer than when you're just trying to write C++ by hand or when you're writing C and just manually doing this math. In addition, unlike Java, this is one notable thing Java doesn't have, is value types versus reference types. A value type is something where the value of the object is its identity. So for example, an integer is a value type. If the integer has the bit sequence 111 inside of it, it should be exactly equal to every other integer which is represented by 111. When we look at reference types, what those are is, say, people. So I have a people object, person object, and it contains a first name. The fact that two person objects contain the first name does not make them the same person. What I care about is the unique identity of the object instance. It gives it its identity, and that's a reference type. In C++, we can represent both of these. We can define a class to be either of these, whichever we happen to need at the point in time. In Java, everything's a reference type, and that's sort of ugly. And in C++, there's a lot of focusing on interfaces and how you use things over how exactly they're implemented. So with C++, we can enforce correct usage. For instance, with the valued reference types, we can enforce that you can't copy a reference type. You can only copy value types. There is, however, C++ 11 added this thing called move semantics, which is, so I can't copy a file descriptor, for instance, because copying a file descriptor doesn't make sense. It's an open file handle. It might be represented as an integer, but if I just copy that file descriptor and then close it both times, bad things are going to happen. If I write to it in different places, it's just not a good thing. So what C++ gives you is a move type. And what moving is basically I can say, I can't have both of these at the same time, but I can move from one storage spot to another storage spot, keeping only one of them ever. And it also allows us to write a lot more efficient things in a number of cases where you have big objects. Like a vector, if you can copy a vector because that does make sense. However, you can also move a vector, and that'll prevent you from having to manually copy all of the data inside of it. In addition, in C++, we have compile time assertions. These are things like type checking and static assert. They make it so that if you're going to try and use this, the compiler will tell you that it's wrong at compile time rather than runtime. So for example, if you give me an integer type as a template parameter, and that integer type can't represent as big of numbers as I need it to be able to, I can yell at you at compile time rather than running into a runtime overflow which you'll never detect. In addition, unlike C, types actually have meaning. In C, you can basically throw away types and it works exactly the same. And you sort of only build types because, oh, I felt like building a struct today. In C++, the types actually have a strong meaning, and you want to live within type safety, and you can live within type safety for almost everything that you do. The more you live inside of type safety, the more the compiler can tell you. The more the compiler can tell you, the less likely it is that your code will be wrong. This isn't strong type safety as in like Haskell, where if it type checks, it's right. Although that isn't even quite true in Haskell. It's just stronger than C. The next really big part of C++, and I talked about this a little bit when I talked about the memory management, is that it has deterministic finalization. Everything has a very, very, very explicit order of construction and destruction, and things happen in a very specific order always. There's one slight exception when you have multiple modules, but you aren't going to run into it unless you use lots of static globals. Don't use lots of static globals which refer to each other, or you'll get non-deterministic compile time errors. Within one translation file, one source file, everything is perfectly deterministic. When you get across them, things aren't. Because of some language issues with trying to standardize that across platforms. So constructors and destructors are the really big things C++ adds to classes. And these enable a pattern known as resource acquisition is initialization, which basically means that if you give me a file, a tfile object, I'm guaranteed, because when it constructed, it can only construct off of a valid file if it opened. And I can build guarantees into my object this way. And when the file goes away, when I get rid of the last reference to that file, it's going to naturally clean up its FD. You can't forget to close the file descriptor. With Python and Java, they tried to get rid of this deterministic finalization and just say garbage collection, yay. They both added it back. So in Python, you have the with statement so that a file will automatically close no matter how you have to exit a block. In Java, they added try with resources. Basically, if I construct something inside of the scope, so if I say tfoo a, in order to instantiate a tfoo a, no matter how I exit that scope, whether I throw, whether I return, wherever I throw, or wherever I return, it'll get cleaned up, and it'll get cleaned up in a fixed known order. Things construct in the order in which they're declared. They destruct in the reverse order at the end of the scope. The other thing is, if you've noticed, I've been talking a lot about the compiler tells you things. C++ is not a one-way street. So in Python, you write code, you run code, and that's how you get feedback on whether or not your code is correct. In C++, you write code, you try compiling code, the compiler will tell you whether or not your code is correct for what it can check for. And there's a lot of work that you can do in C++ in order to try and get things to compile time, so that they'll be fast, they'll be efficient, because the compiler can tell what you're trying to do. And in addition, it'll make sure you try and use them correctly. The biggest thing here is constant correctness. Basically, if I have a constant object, I shouldn't be able to change anything in it. This is really, really useful. I can also call constant functions on constant objects, and that works just fine. In those constant functions, I can't edit my object. So we allow these abstractions, we allow you to use it, and we'll tell you when you're trying to do things that violate your own definition of what's right. C++ doesn't force you to define things. You can get rid of consts if you want to. You can get rid of these different properties if you want to and if you need to because of your specific use case. It doesn't force it upon you. It allows you to use it, however. Circular dependencies, all those classes that magically link together because they happen to know it's Python and it happens to be that everything's a pointer. In C++, that isn't allowed because we have to know how big things are in order to instantiate them. So if you explicitly need a circular dependency, you can do it, but you are forced to notice that you're doing it and cope with it using pointers. In addition, how many of you guys are familiar with sockadder? Sockadder is what you end up using in Linux socket programming. It represents a generic address. It represents any of a half dozen different types of address. It's really, really ugly because they've taken all of these different concepts and collapsed them down into one thing. And so it's good that we have one finite representation, but we want to be able to use it like, I know that this happens to be an IPv4 address. I know that this happens to be an IPv6 address. I know that this happens to be a socket name. It's really good if we can operate on this object with all of those. In C++, when you're writing it well, you'll find when you are building these collapsed objects, when you're building these collapsed designs where I've taken a whole bunch of different pieces of functionality and put them into one object, but it should really be multiple. Generally, you can see this. You can build it that way, but you'll notice that it'll become a lot easier and simpler if you factor things out. In Python, I dare you to try and replace an integer with a date time, and watch how badly things break, and they only break at runtime as you run through your code and go bug by bug trying to fix things. In C++, if I try and do that same replacement, I get type compilation errors. It tells you exactly where everything went wrong. It might be a little bit verbose at times. The error messages aren't always perfect, but it's a lot better than Python where, oh dear God, it might sometimes work, and you have no clue whether or not it works unless you debug every single line of your code again. And then finally, there's the type mismatch errors, like the example with speed earlier. That right there saves you a lot of effort in engineering programming of making sure you get your units right in your raw math. And it all goes away at compile time too, so it's nice and fast and efficient. And then this comes back to the C++ compiler is pedantic, but that's a really, really good thing. It will yell at you a lot, it yells at me a lot. It generates a lot of errors. As long as you're not doing templates, the errors are usually readable. The template errors are getting better, and there's things that are making it easier. Like when concepts eventually comes into the library language, a lot of template code will all of a sudden produce good diagnostics. And you can write templates which produce better diagnostics or worse, depending on how you write them. But generally speaking, when you're writing good C++ code, most things are very, very simple to write. Things should be simple and straightforward. You shouldn't be thinking about bizarre behavior because of this, how some other object works. Things should be nicely encapsulated. Libraries, interfaces should be what you expect. They allow you to do the operations you expect. They don't allow you to do operations which you shouldn't be able to do. In addition, errors are moved to compile time wherever possible because compile time is better than runtime for an error. If I'm building a database, it's much, much better that it doesn't compile than a seg fault. If I get a seg fault, my service goes offline, and all of a sudden I lose millions of dollars because I couldn't process transactions for a day. as I try and find what caused the random little type fault in the middle of my fat multi-million line C++ program. So now I'm going to get into examples of specific C++ coding bits. I'm going to start with very low level C++, which is templates and classes, and then work into a little bit more complex things. Overall notes for when working with C++, the first one is use Clang. I know most of you are familiar with GCC. Clang produces massively better error diagnostics. GCC is starting to learn from Clang, but Clang will give you error diagnostics. They'll give you an error to exactly where it is, color code what sort of error it is. They'll tell you how to fix it a lot of the time. Like, oh, you typed foo, but we know we have a variable foo_b. You probably meant foo_b. In addition, Clang will produce comparable binary sizes to GCC, which are compatible with GCC. It gives you really nice code completion. It's a general library for building compilers and building tools. So in Clang, you can do things like write really good C++ refactoring and code formatting tools that work because they actually know the language, rather than assuming that everything that happens to look like a string, or everything that happens to look like an identifier is an identifier that's valid here. Clang will say, I know that in this parameter spot, I only take integers and only let you code complete those. In addition, Clang fully supports C++ 11 with version 3.3, which should be out in the next month or two. Other general notes for about C++ is don't include needlessly. Including needlessly will slow down your compile. And the other one is that you should put implementation in source files, not header files. The more implementation you put in header files, every single time that header gets included, that implementation needs to be compiled into that module that you're building. This ends up adding a tremendous volume to compiled binary size, or compiled object size, and then when we link all those together, we have to get rid of all the redundancies, and it just slows everything down. There's a lot of tricks you can use in C++ to make things go even faster. Precompiled headers are a horrible idea. Horrible, horrible, horrible. The compiler implementers will tell you so. But there's some things like extern templates that I'm not going to go into, which, if you happen to have a slow compiling C++ project, you can make it faster. The other thing to note is that while the compile time might be slow, the runtime is fast. So you can see sort of a trade-off between compile time versus runtime. Generally speaking, it's okay if the compile time is slow because we compile once. It's nice if we have short compile time so we can do fast iteration. But honestly, compiling, the amount of time you spend compiling it compared to the amount of time it runs in the data center, the amount of time you spend compiling it might as well be longer so that we can get a shorter runtime in the data center. Just as a general theory with tools. Compilers don't need to be really, really fast. However, it's nice when they are. And we can build things like C++ interpreters so that we can compile it faster, which is an interesting subject, and partial recompilation. There are all sorts of fancy things you can do. So the first big thing with C++ is C++ has classes. They first and foremost allow us to define a new type in C++. The new type works exactly like a built-in type. In fact, there's very, very few things that will allow you to actually tell what's different. This is a very good thing. It allows you to extend the language arbitrarily. In addition, this allows for encapsulation of behavior and allowing data types to behave like built-ins, like big int versus integer. And here I'm giving an example of a file class. One of the biggest things that it adds is constructors and destructors. Here I'm defining a constructor or file which takes a name, and presumably that would open the file in error by throwing if it wasn't able to open it. I'll talk about exceptions in a little bit. Then the destructor would presumably close the file, and then we have a write function which happens to write data out to that file. And this is what people see rather than having to manually pass in the FD. The class encapsulates the FD and holds it for us so that we don't have to pass around all these parameters. And then it can call the underlying CSE calls. The next big thing is virtual functions, and virtual functions are sort of an extension of classes. What a virtual function allows you to do is it allows a child class to change the behavior of the parent class and implement behavior, and for a parent class to mandate that a child class implements a specific bit of behavior. In this particular case, I have a class tshape, and what I'm enforcing is that every single shape is able to tell me is able to calculate the area of that shape. I call this getArea instead of area so that you know that it's getting something and it's not changing something. There's some really bad issues when you don't use get and is, where, for example, on a not a lot of the C++ STL things, I can do .empty, and sometimes it tests for whether or not it's empty, and sometimes it empties it. Tell me which one it does. And if it does the wrong one, oh dear God, this is going to be bad. This is why you should name it isEmpty. Or get is empty, or something else. In this case, I make a shape. It says every shape has a function getArea. I'm explicitly saying I'm not defining this function. Other people have to define this function. Basically, you can think of that as I'm setting my pointer to it to 0. C++ will not allow people to directly instantiate this because it has a pure virtual function, which means that you couldn't use it. In C++, I can then make a square shape, which inherits from shape. I could do multiple inheritance if I felt like it. If I needed to, it's going to get the area, which is returning a size times size, and we happen to have a member size. I'm leaving out some bits here like public and private and constructors and destructors for shape just in order to make this more concise. That's fairly common in a lot of my examples. I'm talking about the general shape, not the exact practice of how to do it. What I then do is I make a unique pointer. A unique pointer you can think of like your normal pointer start, except for it makes sure that you delete it. And it forces it and enforces that you can't just copy it. If you want something that you can copy, make a shared pointer, because that's what you actually meant. And I'm using make unique. Make unique doesn't quite exist yet. It's C++ 14. You can write your own. It's very simple and easy. What you would really have to do here is make a unique pointer, open angle bracket, t-shape, close angle bracket, open paren, new, t-square. Really obnoxious compared to this, which makes it so you never have to write new anymore. I'm making it square, and presumably it has a constructor which takes the edge length, and then I can call getArea on it. I'm using it as a shape. So my pointer is to a generic shape thing. I can call getArea, and it'll call the getArea of the square. Sorry. There it is. Just looking at my notes. There's an argument for this one that getArea is not actually a good candidate for a virtual function, and that it's much better served with the visitor pattern. I'll be talking about the visitor pattern later. Basically, you use the visitor pattern in order to encapsulate a specific algorithm outside of the class hierarchy that it visits. You can use virtual functions in order to implement behavior which child classes must provide for a parent class. They have slightly different use cases, but getArea is a very simple to think of example for virtuals. The next really, really big thing is templates. And you should use templates when code is independent of type or independent of some compile time variable that you want to be able to check against. For instance, the dynamically sized list of things. So we know that we have this generic code that we can write for building lists, compact lists of things. We build this class vector, which happens to live in SQL, and we can make a list of tfoos. They allow you to write generic code safely. All of this code is going to be type safe. All of it's going to be type checked. The compiler is going to make sure that you did it right every time it's instantiated. We can also build overloads. So for example, booleans we can store packed very, very efficiently. So when we build a vector of booleans, we really don't want to use the standard vector code. We want to use something very specific for that case. So we can build an overload, an explicit specialization of that template for booleans, which implements booleans really, really quickly. And uses the best way to implement that. Generally speaking, templates allow you to write on anything that matches the general signature. This means for things like, as long as it has a begin and end function, I can operate on it, which is what the SQL algorithm libraries do. In addition, we can choose implementation based on type, which is what standard hash does. If you need a hashable type object, like a map, a hash map, C++ has those, and it allows you to define your own arbitrary hash function for every single object that you're using. The hash function can behave however your application needs. You find this by defining a standard hash, or passing it into the template if you feel like not using standard hash. And there's reasons why you might want to do that. In addition, we can templatize not just classes, but functions. And what this allows us to do is write a generic function. Like, let's say I want to generically calculate the sum of all of the objects inside of a container. I can write that. And soon you're going to be able to write templatized variables with C++14, so I can say, I have this templatized variable pi, which equals 3.14 or whatever. And this should be able to work as a double, as a float, as any of these different integer types and floating point types naturally. And I don't want to have to write it all of those different times for all those different variants with different names, because we can't define the same variable with the same name with different types. In addition, one thing to note is please, please, please don't go read the STL to learn how to write template code. The STL writes horrendous template code for readability. They generally aim for doing things really, really efficient and use really shorthand notations for different things. It's much better to look at examples online. And there's better and worse examples, but generally speaking, examples online will always be better than the STL. If you wanted to do templated code in C, you can. However, you have to use a lot of macros. For example, C, the kernel's vector and list implementation, and GCC's rationale for switching to C++. Their best case was their macros, which implemented a vector. Which they explicitly said, this code is horrible, unreadable, impossible to maintain. If you're trying to do this in C, you have to cast everything with void pointers and things. It's just really, really ugly. And if you are sort of finding it hard to grasp templates, you can very much just think of them as factors. You plug in whatever you happen to put into the template factory, and it gives you out a new thing that looks like that. This is an example from Herb Sutter. Herb Sutter is a big C++ guy at Microsoft who works on the C++ standard committee. This is looking at some old C++ code versus the newer style of C++. This is C++03 versus C++11 if you're familiar with the standards. The first thing is that we can use auto to deduce types. So on the right-hand side, we know that make sure to circle always returns a shared pointer, so we don't need to write that. The second thing is that we use make shared instead of doing new, and explicitly constructing a shared pointer, because that's just cleaner and simpler. And make sure to pass whatever arguments you give it to the class's original constructor. Works with overloads and things. It's nice and happy. In addition, the example on the right is exception safe, whereas the one on the left isn't. So here, all of our pointers are owned by different things. Here, we're hard-coding pointers. With those hard-coded pointers, if an exception gets thrown, they don't delete their objects. Badness happens. We automatically are managing lifetime on the right-hand side. Then the last thing is that we use here, they use a standard for each algorithm rather than for while do, which makes it a lot easier and cleaner to see how you're iterating. And you don't have to focus on what exactly they're at here, where they can do little tricky things which make it different. Instead, we can just say, this is generically doing a for each. If you're trying to read this code versus that code, when you read these for lines in a large code bases written by lots of people, people do other different bizarre things in their for lines. With these standard algorithms, all of a sudden it becomes a generic normalized form. So you don't care about how exactly it iterates between elements. The iterator handles that for it, and you don't have to think, oh my goodness, they did something magical if it happens to hit this case. Then finally, they use a lambda to put into the algorithm, to give it a function to do call with each item. And in this case, they're testing whether or not the pointers match. So that used auto. Here's another example of auto. Here we're going to create an integer. We know 1 is an integer, so if we declare a variable on that same line, it should be an integer. Auto is all compile time, nice, fast, and efficient. We declare a vector of integers. Here we're using an initializer list syntax, which allows us to uniformly initialize anything. In this case, rather than having to make b and then insert 1, 2, 3, and 4 in order, we can just say insert it, just like how you'd expect it to look. You can define initializer lists for your arbitrary types that work however you need them to. There's also some standard initializer list things that auto-construct given your constructors. Here we're defining a lambda, which takes a parameter and returns a boolean. Then we're saying, here's an iterator. This auto is mainly just an example. To show auto, really this type is going to be standard : vector of int : iterator. That's really, really, really obnoxious to write. Auto gets rid of all of it. and then we use a standard algorithm to say, if any of the items inside of this list happen to cause this function to return true, and that's going to happen when x equals 2. So for the second item on the list, print out hello world 42, and we can make this compile in C++ by overloading operator comma. Really a horrible thing to do, but it's sort of cool that you can. Normally, comma-separated lists just specify that everything inside of the comma-separated list will be evaluated, and the first or last thing will be returned. I don't remember which. Generally speaking, comma-separated lists aren't things that you use very much in C++. What comma-separated lists are useful for is inside of a for or something where you only have one statement, and you need to say multiple things. For memory management, if you remember that those slides from Sutter, we don't need to use raw pointers anymore. We don't need to use new and delete anymore. You can just use unique pointer and shared pointer for pretty much every one of those cases. Or even better, make a local object inside of the class. Don't make a pointer to an object, just say, I want a food right here on the stack now. Most of the time, that's what you mean. In addition, you can choose where you want the data, heap or stack. Every single class you can instantiate on the heap or on the stack. It's completely up to you. We're not going to force you, like Java does, to put everything on the heap because you can only allocate objects on the heap. Bjarne Stroustrup says that C++ is the best language for garbage collection, principally because it creates less garbage. When you're writing really nice, clean C++, deterministic finalization and things, make it so that you don't need to build all of these big pools in order to manage your memory. We know when things live, we know when they go away. They just naturally go away, and so we don't waste space. Another thing is if you're used to copying, if you have an object which contains an object, there's two different ways that we can copy this. The first one is a shallow copy where we just copy the outside object and then point to the inside object. The second way is a deep copy where we copy the entire stack of objects. In C++, when you're writing your classes, you can define exactly how they should copy. There's a default behavior which you can override or get rid of if you don't want to be able to copy at all. But you can choose exactly how your data structure should copy, which is nice to be able to do, unlike a lot of other languages. Lambdas, which we also saw in that example, simple lightweight functions declared inline. They have a nice handy syntax. Very, very short. You could just write auto here, and all of a sudden it becomes a templated lambda, and we'll take anything, and as long as they are comparable, everything works. It's cool and pretty, and really easy to write. We can also specify a return type, which is what this one's showing. So this one's explicitly saying return type bool. This one will automatically figure that out. The advantage of explicitly saying what your return type is it makes error messages a lot more readable. The compiler will produce horrible diagnostics if you use that wrong. Nice diagnostics if you use that one wrong. Specifically, if the inside of this returned something other than bool, and then you call the function which expected the function to return bool. Also here, we're doing a capture. So inside of the square brackets, we can capture arbitrary variables from the surrounding context. We can capture by value, by reference, and soon by move. If we capture by value, this basically copies the value into the function, which means that we could pass this into some arbitrary thing which doesn't know anything about our data type, and it would be able to compare against our set point whatever the value is, which is really handy to be able to do for encapsulation. Next thing I'll look at is sorting, which is another example from a Stroustrup presentation. In fact, the same Stroustrup presentation. And this one's an example of why you shouldn't use C in a lot of cases. So he's looking at the qsort function. Qsort function is a standard library function for sorting things. People use it all the time. People think that it's really good style in C. He's going to point out why this is quite so horrible. So first, you're giving some arbitrary big block of memory, and it may or may not be what you expect it to be. Secondly, you're telling me exactly how long it is. Shouldn't that be part of your object? You're telling me how big each item is. Shouldn't I be able to figure that out? You're giving me a comparison function as a function pointer. I can't inline this if I'm a compiler. I can't make this efficient. Also, isn't there standard comparisons defined for your elements? Wouldn't that be nice to use? When I'm using this, it doesn't know how to compare doubles. It doesn't know how big a double is. It should be able to know these things. When you're writing really clean, simple C++, the compiler should do everything that it should possibly know how to do. It knows how big a double is. It knows how big a char star is. it can do these things at compile time, and when you're writing with C++, you shouldn't explicitly have to specify them. So we can keep on going. Mostly, as I mentioned, we're throwing away type information. The type information can be very, very useful because we're going from this known types to generic types, and when we call the comparison function, we have to go back to specific types. That's really, really ugly. In C++, we can go type safe the whole way. This is the part of the implementation of qsort, and I challenge any of you to try and find bugs in this and understand it trivially about what algorithm it uses. It's really, really ugly. First and foremost, we can only swap plain old data types. We can't use this on reference types. That's annoying. We're manually doing byte manipulation and pointer manipulation. That's very, very unsafe, and we're very likely to get that wrong if we happen to get our math wrong for how big things are. We're calling all of this function pointers over and over again, which is really, really slow. For whether or not you think this is an unfair example, generally speaking, he didn't make this up. It's part of the standard library. People like writing C code that looks like this because it's nice and generic and simple. I don't think it's quite so simple. People write. Stroustrup's actually a teacher at a university, and so he sees it as he goes around places. And in addition, people think that that's more efficient than when I write it in C++. It's not. The C++ version is going to be an order of magnitude or two faster because it knows more. The compiler can do things to optimize it better. And in addition, he complains about C++ people using bad coding style. And he really likes complaining about people using bad coding style because people use bad coding style. But yeah. And they say, he says bad coding style is not always the student's fault, which is very true. A lot of things that you find online, if you're looking for C++ tutorials, look for C++ 11 tutorials. Look for new code tutorials in C++. The old C++ is very different. 11 makes a lot of things simpler, cleaner, and easier. And there is a lot of really bad code on the internet. There's, for example, if you're familiar with the person who made Braid, he asks some C++ questions sometimes. Most of them are examples of really, really bad C++ style. For example, he was asking a question about making something disappear at the end of a scope. Well, the easiest solution to that is to just declare it locally. If you really can't do that, the next solution is to make unique and use a unique pointer. And he was looking for a lot more complex things. And then there's also a scope paired concept, which is sort of cool to solve it. So what should this look like? We should just have a sort function, you give a container, and it just works. In C++, we can't quite write this, but we can come awfully close. We can write generic ones for like vector and things. And that's very nice and simple and easy to use. We aren't specifying all of this useless information that the compiler already knew. We know how to compare strings because your string must have a comparison function in order to call sort. We can just use your comparison function on your string class. Your string class could be an arbitrary class, which just has an arbitrary comparison function. It still works. And it goes massively faster. And in addition, we type check, which means that you're it enforces that you make less error. It enforces a whole bunch of rules about the language and gets rid of entire classes of errors. In addition, we can't possibly leak because we have raw pointers without having a garbage collector, which is how a bunch of other languages get rid of memory leaks. There is an argument for adding a garbage collector to C++, but it's not necessary most of the time. And in the cases where it is, where like I need this big pool of memory, which is a cache, we can actually write that in C++ with a garbage collector. Containers. So C++ has a whole bunch of built-in containers, like Python does, and like all of the other ones do. Vector is a variable length list. Array is a fixed length list. There's array is a fixed length list at compile time. There's a dynamic array which is coming into C++ 14, which gives you a fixed length list specified at runtime. So when you first construct it, it takes a very specific length, and then you can't expand it, which is the same as C99's variable length arrays. However, it's an expansion upon that concept. and it makes a couple things safer with it. Map and unordered map are hash containers. Generally speaking, you mean the unordered container. The ordered one keeps elements in the order that they naturally sort, so you can iterate through them in the sorted order, which generally you don't care about with a hash map. Multi-map says I can have multiple keys with the same value. Queues, stack, and priority queue, they're just useful to have. We also have, so in C++, in addition to pointers, it introduces this concept of references, which you can think of as sort of pointers with a different syntax. Unfortunately, references can be null, which is really, really stupid, but it's a side effect of how they're implemented. However, what references do is they allow me to not have to use pointers when I'm passing around things. They allow me to interact with them like they were local, without them actually being local. So for instance, I have a struct which has a really big thing in it, and I want to return this really big array of 2,000 ints, and I want to do that without copying or anything. I can return a constant reference to it, and this guarantees that, one, you can't edit it, you can't modify it in any way, shape, and form. I'm also not copying.
Why does that have the keyword const in there twice? Is that intended?
Oh, for here and here?
Yeah.
So what this first one is doing is this is defining the type, and then this second part right here is saying that the function operates on a constant object. So if I made that function non-const, if I have a const t big, so if I have a constant t big, I couldn't call the function. By having that function be const, if I have a const t big, I can call the function because the function guarantees that it doesn't modify the t big. Then here is a similar thing, but I'm taking it in as a function parameter, a constant reference. The advantage of constant references is nice and safe, doesn't copy, cool, efficient. The only time you really shouldn't be using constant references for passing parameters is if it's like an integer or something that's smaller than a pointer. But here, same thing. So the standard STL algorithms library has a for each implementation. However, C++ also implemented a for each syntax for for loops. So I can say, here's a vector of points, and if you notice, it generated a nice initializer lists constructor for me, so I can just generate my points by initializing them exactly how you want to, and how you think is natural. And then what I'm going to do is iterate over every single point. So auto will bind automatically to the t point. I can explicitly say I want my auto to be a constant reference. I can also explicitly say I just want it to be constant or just a reference. This makes it so that I can guarantee that the auto doesn't copy. If you don't write const reference here, you can massively lose performance for code that looks right. It's sort of a gotcha. There was a funny Stack Overflow example where someone said, hey, I wrote the old for each loop and then I wrote this, and it went 4 orders of magnitude slower, and it's because they forgot the constant reference, so they were copying it on every element. And then here, with each point, I can just use the point how I wanted. I've completely hidden all the syntax and all the bits around how exactly I iterated. It's just naturally done. But exceptions allow us to throw errors we otherwise couldn't return. They also allow us to not have to compact all of our errors into an integer error code, and we can attach additional data to our errors. So inside of C, when you're making system calls, you get an integer back, and then you can go check error node to find out what sort of error was it. The thing is, though, error node doesn't tell you very much most of the time. Most of the time, I want to say, I had an error reading from this byte because I hit the end of the file. C doesn't give you that level of detail. In C++ with exceptions, you can build that level of detail if you want it. We can also catch specific classes of errors and let other ones pass. For example, if I want to catch file I/O errors and cope with them, I can do that, but let out-of-memory exceptions pass. And for instance, one really famous example of why error codes is really bad compared to exceptions is I want to convert a string to an integer. In C, this is the A2I function, and it returns 0 in case of an error. This means that you have to inspect the string, test whether or not it looks like 0. If it doesn't happen to look like 0, then I need to call error node to find out what went wrong. In C++, what we can just say is we throw an exception if we happen to get it wrong, so we don't have to try and make it a reserved state when we don't have one. In addition, with C++, we can greatly reduce the level of boilerplate repeated error code. For instance, if we're doing lots and lots of file I/O, every single time you make one of those syscalls, you should check for an error code, and you have to handle if it errors. In C++, we can just throw if it errors inside of our generic read handler, and all of a sudden, you can just write all of your code and deal with all of the file errors particularly, or you can deal with them in specific cases using your try-catch blocks. And the last really big thing is it enforces correct usage. This goes back to examples that I've given before of a file descriptor. In the case of a file descriptor, we can't copy it naturally. You shouldn't just be able to say, I have a file descriptor, copy it. That doesn't make sense, even though the C integer variant lets you do that. However, we can say to duplicate it, which is slightly different than copy. It has a different meaning. We're making another entry point to that file. In addition, the file descriptor can make itself close when it's done, and we have a lot of different ways of creating file descriptors. We can create overloaded constructors, or we can just take a generic integer, which is the result of a system call. In a TFD class, we can enforce all of these rules that we want. We can also make it implicitly cast integer when you need it to. So you can just use it naturally in system calls how you're used to using the integer, so that there isn't really overhead. In addition, we can say, so I have an FD, and I want to set it to be a new FD that I just opened. When this happens, we can swap them, and we guarantee that both of them are going to close properly. In C, you can just replace the integer arbitrarily, and the old one won't close, and the new one will just sort of replace it, and you'll have an open leftover file. This is bad. In C++, we can enforce these rules. And that's about it for generally how you write C++ and things. Anyone have any questions on all of that? Any random bits of syntax that I happened to just show that I didn't talk about that you were interested in?
Oh, do you have any, like I've mostly done C so far, and I'd like to get into this. Do you have any good resources that you would say are reliable in terms of teaching you right?
There's a couple. Let me jump through
time and space.
Time and space.
So for C++, so the biggest thing is make sure that you're using a new tutorial. I like cppreference.com. It's a wiki which documents all of the C++ standard library and how to use it. So for example, if you look at the vector pages, they give you examples of how to use it. C++ has mutexes and locks built into the language now. They give you good examples of how to use them. Also standard thread. C++ in 11 added all sorts of concurrency features which are cool, which I'm not going to be talking about. The other thing is to listen to talks by really big C++ guys. Bjarne Stroustrup gives a lot of talks on C++ and C++ 11. Most of them are very good and well put together, and they tell you how you should build things. Same goes for Sutter, who's Microsoft. In addition, if you're really, really interested in C++, there's a site isocpp.org, and you can actually follow this progress of the standard. The standard is developed by a committee which has open meetings a couple times a year, and anyone's welcome to go to those. Which is interesting. If you get really deeply into C++, I wouldn't recommend them for the faint of heart. The other thing is that if you're writing C++ code, I'm willing to review it. If I say your code is horrible, don't be offended. I know I've done some code reviews for people's C++ code in the past, and they've come out very, very unhappy with me, which is understandable. The odds are that there's a lot of things that you can do differently. There's also a certain extent to when you get to fancy C++ about, there's different theories of what looks better, where both things are functionally equivalent, but what looks better is a matter of opinion. I won't code review your entire compiler class compiler. That's just a lot of code and I'm not interested. However, I will code review small little things, like one specific header, or one specific C++ implementation of something to see whether or not it looks good. And you can contact me at my CS email address, which is what you think it is. Since I'm about to graduate, and my TCC one does odd things once you graduate.
And you have to go talk to them, otherwise they make it.
You have to get an alumni account instead, which is a different address than your TCC account, and the TCC one goes away.
Yeah. Well, even if you're a graduate student, you have to talk to them, otherwise it's made.
but more or less, yeah. CS accounts, they stick around forever. Yay! So for miscellaneous insights, the first one, and this one will actually come up when you take compilers. This will probably show up on your entrance exam for C++, is that base classes require virtual descriptors. Why this is so is say that I have a class tfoo, and I have a class tbar which inherits from tfoo, and then I make a pointer to tfoo which is actually pointing to a tbar. So this is the same as that shape example before, but where I made a pointer to a t-shape, but it was actually pointing to a t-square. In this case, which destructor is going to get called if it isn't a virtual function? What's going to happen is it's going to say, I know this type is foo, I know foo has this destructor, and I'll call that tfoo's destructor. And that is not the behavior that you want. tbar's destructor might have done something magical. So what you say is that if tfoo has a virtual destructor, it will always call tbar's constructor first, and then it'll call tfoo's constructor afterwards, which is the behavior that you want. There's actually compiler flags to enforce that you do this. They can't check for every case, but they can check for a bunch of them. Another thing is vectors versus lists. So a vector is a packed data structure. A list is you have pointers to each element. Generally speaking, vector is faster by several orders of magnitude. Because the cost of iterating over the list, of dereferencing all of those pointers and reading all of those blocks, is far more than the cost of just directly accessing them using pointer math, which is what a vector does. Although it doesn't use pointer math handcoded by the programmer, it uses pointer math generated by the compiler. Even better. About the only case where a list is faster is when you just push at the front over and over again, because this means that the vector is literally in its worst case. And there's online benchmarks which show this, as well as in Bjarne Stroustrup, he talks about it with that object-oriented versus packed structures. He happens to mention it. The next big thing is the visitor pattern. What the visitor pattern is I have a class hierarchy usually, and the base class says I have the base class basically defines the group of shapes. So I have a base class t-shape, and then I have a circle, a triangle, and a square. Rather than write a virtual function t-shape to do something like print them, so I could say all shapes must have a print function, and then every single one of those shapes has to print. The truth is that there's many different ways that you could print. So probably what you want to do instead is we want to consolidate all of the knowledge about how we happen to print these to an external class which will just generically look at the objects and print them. So what we do is using a visitor pattern, and what a visitor is going to do is I make a class which will accept all the different types. The actual code to make visitors in C++ is a little bit interesting and wonky. It takes a little bit to get used to it. There's one little bit of unsafe behavior that you have to do in order to be safe on either side, because you have to go from generic type list to type safe. And so visitors allow me to write this generic algorithm outside of my classes, which operates on a class hierarchy. They're really cool and useful, and way better than virtual functions in a lot of cases. Because we can consolidate all of this to, I have an XML printer, I have a JSON printer, I have all of these different formats of printing. We write the algorithm in one place instead of having the algorithm scattered all over our code base, is basically the concept. Next one is variadic templates. Some people think these are crazy magic. If you're trying to serialize or deserialize something, they're exactly what you mean. So for example, I could be saying, I want a type-safe printf. Printf currently works type-safe because the compiler happens to know magic that it's printf and does lots of crazy introspection. That's what you get with a standard C compiler nowadays because everyone was writing printf wrong, so they built it in. With C++, we could just write a type-safe printf to begin with. Basically, here, in this one I'm not using a format string, but we can say we accept a generic group, a generic list of types, and this is saying I'm pulling one item off of the list at a time, and then I have the rest of the list of types, and then I just recurse, unpacking the rest of the list of types, and then we also define a base case to say when I don't have any types, do nothing. Generally, you'll see with recursive templates or variadic templates, there's two patterns that are used. One is a variadic template as a wrapper function, which is when you saw make unique and earlier, that's what it was doing. It was basically doing perfect forwarding of all of the arguments to the class constructor. Or the other option is that you're doing something like this where you're recursively pulling off one element at a time. But if you want to serialize something, this is exactly what you mean for serialization. You basically just say, this is how you serialize this type, and then I can generically serialize a list of types. Another thing is, how many of you know the difference between A++ and ++A? What do you think the difference is? Does anyone want to answer that? Go.
Well, if you do post increment, it makes a copy.
Yes. But if you do ++A, it's going to increment A and return A. If you do A++, it's going to copy A, return the copy, and then increment A. This means that you might be copying something very, very expensive. So generally speaking, you should use ++A in almost every case. You might be used to writing A++, you should get yourself out of the habit because you might accidentally copy something and massively set it on your code for no good reason with a useless copy which you're just going to get rid of. The compiler might be able to optimize it out. There's a decent chance if you're using complex classes it can't. So for example, for for loops, you should always use ++A or ++I instead of I++. Even better, use for each loops. These are some points that I'm not going to give specific slides for. The first one is that low level is not necessarily efficient. You can see this in the standard sort example and qsort. We can use these SQL algorithms, and using the algorithm is actually going to be more efficient than hand coding it because the compiler can inline and see types of things. So higher level C++ code is actually generally faster than C code because the compiler knows more. And the more the compiler knows, the better it can do at optimizing. Using standard algorithm, we can make a lot of control flow a lot simpler. For example, if you need to find the index at which this condition is true first, or I want to call a function with whatever element this happens to be true for, a C algorithm has things to do that. They're a lot easier than if you're hand coding a loop and then writing jumps out of your for loop. Then finally, we have in C++11 a whole bunch of asynchronous stuff. You no longer have to use pthreads in order to make threads. They're all nice and type safe. It's all wrapped up in a standard thread library. We can also do asynchronous launching of functions and things, and futures to say, I eventually will have an integer, but right now I just have a thing that'll give me the integer eventually. Then finally, we can use precise casts. So C-style casts have 4 different behaviors which might implicitly happen based on what you have to have written. This is really, really bad because it's not entirely predictable for you as a programmer unless you have memorized the spec. In C++, you should generally disable old C-style casts because they're bad, and use the 4 specific casts which they break apart into. Static cast, dynamic cast, reinterpret cast, const cast. Const cast allows you to remove const. Reinterpret cast allows you to say, this pointer is now that, and I don't care. It's basically treat a pointer as some other arbitrary type. Dynamic cast does runtime type checking. As long as your things have a virtual function in them, that means they have a vtable. As long as they have a vtable, we can tell what in the world the type is at runtime. And we can compare whether or not the types are equal at runtime quickly. Reinterpret cast will return null if you happen to do an invalid cast, or will return a valid pointer if the cast is applicable. Dynamic cast, that was dynamic cast. Static cast. Static cast is a basically compile time safe cast, roughly. We know that we can make this sort of cast. You can use it for going up and down in class hierarchies, if you know that it's safe. So all of that was all stuff that you can do now for the most part, other than make unique. C++ 14 is hopefully coming out next year. They have a fairly finalized draft at this point, so it's on the right timeline. The biggest thing that it adds is an optional type. So no longer do you have to use null pointers to say I either have something or don't. You can use an actual optional type, which adds another state to the object, which doesn't have a value currently. Variadic type templates, which I talked about earlier. You can make a pi, which is a double and float, and all of these other things, and you have one name to refer to it by. There's this concept in C++ 11 called constant expressions. What a constant expression is it's a compile time expression, which means that you can do assertions and things around it in compile time, which is really, really cool and clean and cool. However, currently, as the spec is written, it's very, very constrained as what you can do. It's basically a one-line function which has a return in it only. In C++ 14, they're relaxing the constraints considerably, so you can do ifs and then whiles, and you can have local variables and things. In addition, there's libraries coming for doing all the standard things we're used to: networking, shared locking, so read-write locks, more complex threading things, polymorphic lambdas, which is where you just write auto as the lambda argument type and it becomes a template and it just works, because we can always figure it out. Further down the timeline, which is probably going to be C++ 17 or C++ 20, is when we'll really get the networking library. Modules. Modules are a different way of compiling C++. So if you're used to Python's import statement where you import a module, basically that's being added to C++. Rather than the header and source file model, you write everything in one file. You say this is public, this is private, and then the compiler will pull it apart into the header and source file for you. We also then don't, by including one header, get all of the headers that it includes. How headers are implemented is pretty much just copy and paste entire header into my text buffer ahead of my program and interpret it first. This is really, really slow. Modules allow us to reuse things, and they massively improve compile time. And if you're interested in what's sort of coming up in C++, isocpp.org has everything. And then that's it, pretty much. That was 14 minutes.
That's good.
I definitely saw that talk with Bjarne, and was very happy about things. Because I like if I remember correctly, the first 20 or 30 minutes of that talk was just him complaining about other people running C++ wrong.
Pretty much.
Well, if you're a guy who invented it, then it's got to hit you in the right nerves when you see people writing crap together.
Yeah.
But, yeah. Another thing that I didn't talk about very much that I thought of talking about is Herb Sutter has been talking a lot about recently. There's been a renaissance of C++ and more interest in C++. This is partly due to C++ 11, but it's also partly due to a single core has hit a wall, the power wall, and so single cores aren't getting faster, so they have to write code efficiently. With C++, or with data centers, about 88% of the cost is directly related to computation, and if you can compute faster, if it takes you half the time to do the same computation, half the power, half the resources, you'll pretty much have your data center costs. And if you're a Microsoft, if you're a Google, if you're a Facebook, this is millions of servers, you're saving millions and billions of dollars in operating costs by doing this.
Does C++, does it work as a good language for doing multiprocessor? Just like a lot of people are trying to push for languages that are just that domain specific.
It's not ultra domain specific for that because you're going to be hand coding how you want to parallelize it.
Mm-hmm.
They're looking at adding it to the language. We'll see whether or not it actually happens.
Yeah.
There's a lot of people, like Intel has built specific threading libraries, Silk++. Microsoft has built a whole bunch of threading libraries for C++ in order to add more advanced threading abilities to it. It's not the ideal language, but the thing is it allows you to work exactly how you're going to need to work it. Usually, if you want to write really efficiently and not care about how you're going to build or something like that, you do want to look at a higher level language in C++.
Yeah.
Like you want to transparently distribute across, go from a single machine to transparently across an entire cluster. C++ is not going to allow you to do that. It's too close to the hardware.
Another thing about C++ that it does that, like, for instance, C doesn't do is namespaces. Right? Namespaces are particularly useful if you're doing a project involving specialized algorithms.
So what that one is that if you're used to writing C code, you include a header, and they prefix everything. So for example, if you use the Cairo graphics library, everything starts with Cairo underscore. This is really annoying because every single time I call every one of those functions, no matter what, I have to write Cairo underscore. What C++ namespaces do is they give you a language, a way to do that sort of behavior inside of the language. So with a namespace, I can say I have a namespace Cairo and I define all of my functions. They'll live inside of my namespace so I don't conflict with other people's functions. When someone's using it, if I'm only using one thing named Cairo, I can just say using Cairo, and all of a sudden it'll resolve the Cairo : for me. It'll pull everything that's in the namespace Cairo into my local scope.
When I first started doing C and realized that namespace was, there was just one namespace. Well, that got a lot worse.
Really quiet.
So, I'm not familiar with C++ syntax. What does the : mean? :
is compile time lookup of some thing. So if I have a class and then I do : I'm looking up inside of that class something. So it could be a type name, it could be a static function. It's something doing it without an object. Note you can also use dot in order to do these static things without an object, which is just sort of funny.
Do you know why they chose : ?
It looks weird.
Yeah, it looks ugly to me, I don't know.
It's because they didn't want to use one colon, I think, because of ternaries or something like that.
I don't know exactly. Note, however, there are some cases in : where you can't use it. Like if you have to explicitly call it a structure. So I explicitly made a shared pointer, and I'm doing my own allocation and deallocation into a memory buffer, which I've pre-allocated of that shared pointer. I can't call standard : shared pointer on it. Standard : doesn't parse. So you have to use a namespace standard, and then you can just call tilde shared pointer. You can also use namespaces inside of function bodies. You don't have to do it for an entire module. Also, never use using inside of a header. That means that you force everyone who includes your file in order to use your using, and that's really bad.